According to IBM, more than 90% of the data was produced in the last 2 years. And this explosion of data is likely to grow exponentially in years to come. To handle such a massive amount of data for better insights, the businesses are constantly making use of different technologies like data science, machine learning, artificial intelligence, and quite a few others. They all have one thing in common, and that is they all act on data. If you want to build applications that are data centric, the sensible choice nowadays is to use the Python programming language because it comes equipped with some standard libraries that facilitates the development of data science applications. Besides that, the Python programming language is extensively used in developing dynamic web applications as well. Hi, my name is Mohammad Rizwan. I am a software engineer with over 15 years of professional software development experience. In this short course on Python technology fundamentals, I will show you how we can download and install Python on Windows operating system and how to get started with PyCharm, the free cross-platform IDE for Python developers. I will introduce the basic rules, syntax, data types, keywords, and best practices of the Python programming language. And since Python supports object-oriented programming paradigm, I will describe how it implements concepts like encapsulation, inheritance, and polymorphism. Python is the fastest growing programming language in the world because of its simplicity and ease of use. My goal for this course is to get you up and running quickly with the Python programming language by making heavy use of illustrations that help remember the key language concepts. I hope you will enjoy this course, and do remember to subscribe to this channel to receive latest updates. So without any further ado, let's get started. So before we actually dig deeper inside the Python internals, it is very important to get an understanding of the Python principles that makes this programming language stands out from others. The first among those is that Python is an interpreted language. Interpreted means that the Python code is not compiled directly to the machine language. Instead, it is interpreted at runtime by the Python interpreter. This is what makes the Python programming language portable across operating systems because it does not require the source code to be compiled for each operating system. This also distinguishes Python from other programming languages in that all other languages requires the use of compiler to first compile the program in a machine readable format and later execute it. Python, in contrast, directly interprets the source code at runtime. This is one of the reasons why it is commonly known as the scripting language. Another important principle of Python is that Python has an extended support for object-oriented paradigm. The object orientation in Python lies in the fact that everything in Python is an object. To better understand what an object means, consider it in the context of the real world objects. Like for example, in my surroundings, I can see a couple of objects like a mug, an apple, a light bulb, and many others. So these objects have some state, like in the case of light bulb, it's switched off at the moment. That depicts its current state. And it has some behavior, like we can switch it on or off. So the current state of the object as well as the accompanied behavior that when triggered alter the object's current state by doing some internal processing is how we perceive objects in the real world, and Python is no different. In Python, we can create objects that encapsulates state represented by its fields and behavior represented by its methods. We define classes as a blueprint from which individual objects are created. So consider this bulb class as a factory that produces objects of type bulb. And each object created this way manages its own state independent of others. We discuss more on the object-oriented aspects of the language later in this course. Python has an added support for functional programming as well. By this I mean to say that the Python language treats each function as a first class object, and with this capability the functions behaves the same way any other object in the program does. Like it can be assigned to a variable as a literal, it can be passed as an argument to the function, or it can be returned from the function as its return value. Please don't hang up to it if it doesn't make sense to you for now. It will get super clear when we talk about functions later in the course. Python is a dynamically typed language. What this means is that the variables that are used to hold values does not require to be of any specific type, and that the same variable can hold values of different type during the program execution. So the language does not mandate the explicit data type declaration for the variables. Don't panic if you have just stepped into the programming world and all we have discussed so far seems daunting to you. I will try my best to discuss all the nitty-gritty details of the language as the course progresses. Python supports the use of declarative programming style in addition to imperative programming model. Declarative programming is a way to give instructions to the program in terms of what to do, not how to do it, as we normally did in case of imperative programming. Doing so makes the program super easy to read and write, and this contributes to one of the reasons why the Python programming language is gaining popularity with time. In Python, memory is managed for us so that we do not have to delve into explicitly managing it by ourselves. In Python vocabulary, we give a special name to this automatic memory management, and it's called garbage collector. When we create new objects in the application, Python allocates memory for us, and when we are done with the objects, it sweeps up the memory by destroying objects that are no longer referenced, resulting in recovery of the used memory space. Like natural languages, in order to speak the Python language, one must be aware of the language vocabulary. These are some of the terms that I will be using frequently throughout the course, and it is very important that you must get hold of it before moving on to avoid any misconceptions during the course. We write our code in text files and later save the files with .py extension. Each file created this way is a module in Python. Types in Python refers to the class of the objects. I have just illustrated this fact that classes acts as a blueprint from which individual objects are created. Object simply refers to an entity that holds data. Variables in Python are used to hold references to objects. All fields and methods of a class are called attributes in Python vocabulary. Callable attributes refers to the methods of the class since these attributes are defined once and can be called from different parts of the program. All modules that are made available to us by Python are packaged up in a standard library. Blocks in Python are the set of statements that are enclosed within a function. Suite refers to the statements that are part of the conditional and looping constructs. Scopes in Python refers to the visibility of the variables during the program execution. Sequence in Python refers to those complex objects that exposes an iterator function that we can make use of in our code to iterate over its elements. A statement is a unit of code that a Python interpreter can execute, and an expression is a statement that evaluates to a value. Consider these statements and expressions as individual lines in the source code. I understand that these terms do not make sense to most of you for now. Don't worry and bear with me. I will try to uncover each and every detail as the course progresses. Installing Python on Windows operating system is very simple. Just go to the downloads page of Python's official website at python.org/downloads, and under the Downloads tab, click the button labeled Python 3.9.1 to download the installer. This is the most recent Python version at the time of this recording. It may have been changed by the time you see it. Once the download completes, locate the installer on your system and double-click to install it. It prompts you upfront to confirm whether you want to go with the default Python settings or you want to customize Python by extending it with additional features. Customizing Python is beyond the scope of this course, so we will be going with the Python default installation. But before heading towards it, we must have to select this checkbox that says Add Python 3.9 to path. This is a way to tell the installer to register the Python installation path to the global namespace of the operating system. This way we need not to provide the whole path each time we were to use the Python commands elsewhere because the operating system is now well aware of it. Next, click Install Now. It goes on and install Python on your operating system. Once done, the next step is to verify the Python installation. Open the command prompt by typing cmd on the start menu and type python space dash dash version and press enter. It says that the Python installed on my machine is 3.9.1. If you are presented with the Python version like this one, then congratulations, you have successfully installed Python on your machine. Next, we have to download the text editor that not just assist us in writing Python code, but also to help us out in running the Python programs. There are quite a few to choose from, and I go for PyCharm IDE, the most dominant IDE in market today for Python developers that not just help us out in writing code, but also to run debug and to do a bunch of other stuff, all abstracted away from developers, and hence let us focus more on the work at hand and automate the tasks we are least concerned about. So to download the PyCharm IDE, go to www.jetbrains.com/pycharm, click download, and here on this screen click the download link that corresponds to the community edition. This will initiate the download process. It takes some time to complete downloading, and once done you will have an executable file downloaded somewhere on your system. Just double click the executable to start the installation process. It presents a couple of screens up front before proceeding with the installation. Click Next on this screen to continue with the installation. Accept the default installation folder for now and click Next to move on. Here I would like you to check this checkbox. It will basically create a shortcut of PyCharm IDE on our desktop so that we do not have to go deep inside the PyCharm installation folder each time we want to start the application. Click Next and finally click Install. It goes on and install PyCharm IDE on our system. Once the installation completes, it presents another screen letting us know that the IDE is successfully installed on our system. Now, if we want to start PyCharm right now, we can check this checkbox and click Finish. The first time the IDE starts, it prompts us to import custom PyCharm configurations that we might have exported from other PyCharm instances, or to go without importing any settings. We will be going with the default settings, so click on the OK button to proceed. When we open the IDE for the very first time, we have been presented with the screen like this one. One thing worth mentioning here is that every Python application lives in the context of a project. So to create a new Python application, we have to create a new project. To create a new project, click on this plus icon. A screen appears asking for the project name, the part after the last backslash. The preceding path shows the location where this project is eventually going to be stored. I am going to name it simple application, but you can name it whatever you want as long as it does not have any spaces or special characters in between. I have named it with the lowercase first letter and use an uppercase first letter for each subsequent words in the name. Though it is not required, but it is considered a good practice to name the project this way, a syntax sometimes known as a camel case. Below it shows the path to the interpreter that will run our application. Here, if we leave this checkbox as checked, then a file with the name main.py is also created for us along with the project. Leave it checked and click create. It went through some prep work, and once done, a project is created with a sample main.py file within. Recall the Python jargons we discussed earlier, where I stated that each text file created with the .py extension is a module in Python. So here main.py file is a module and all our code goes in these files that ends with .py extension. Furthermore, a project can contain multiple modules and we can harness the code of one module inside another. In addition, we can execute each module individually or it can be executed as part of another module. We sometimes refer to the file that we execute directly and not as part of any other file as a script. This is the editor window where we will be writing all our code, and here is the project window that lists down all the projects we created or otherwise imported inside PyCharm IDE. Now this main.py file with some sample code in it gives us a chance to discuss a couple of points here that will help us to better understand how the Python interpreter went through the execution of the script. First, click this red circle to disable the breakpoint. This is something to do with the debugging of the application, which is beyond the scope of this course. Also, all lines start with the pound sign are called comments in Python and are ignored by the Python interpreter. These comments are used to add notes in our natural language to summarize the working of the code. Furthermore, you can see here that some statements are indented and some are not. So here is the rule. All statements that ends with a colon is a way to tell the interpreter that it wraps around all the following indented statements and that these wrapped statements will only get executed with the consent of its owning statement. The style guide for Python code recommends a 4 spaces indents. For now, it is suffice to think of the owning statement as header and the following indented statements as body, and that the header wraps around its body. The interpreter starts from the beginning of the file and parses the code line by line in sequence. Since line 1 is a comment and we conclude that these comments are there only for human consumption, so the interpreter safely skip all comments it came across during the program execution. It then moves to line 2. Since there is nothing here to parse, it jumps to the next line. Line 3 and 4 again are comments and the next two lines are empty, so it jumps to line 7. Here it came across a statement that starts with the def keyword. This is a way to define a function in Python. Functions in the programming world are used to group multiple statements together and further give it a name. Once we define the function this way, it can be called from other parts of the program by its name, and all the statements it wraps around gets executed in turn. So here this statement says that define a new function, name it print underscore high, and only execute its body when this function is called by its name from elsewhere in the program. So when the interpreter came across this function definition, it knows that these statements will only be executed when someone invokes this function. So it safely jumps to line number 13. Here we have a condition in place that checks to see whether we are executing this module directly or execute it as part of another module. To demonstrate this concept, let's create another file in the project. Right click on the project name and under new, Click File, name it test.py and press enter. Call the built-in print function here and provide it some text for display on the screen. The text should be wrapped inside either single quotes or double quotes. Print is a built-in function that is made available to us by Python, and the purpose of this function is to display the provided text on the screen. Now we can include this module inside the main module in order to make use of the code defined in this module. To include one module inside another, we have to use the import statement at the very beginning of the file. The import statement starts with the import keyword followed by the name of the module that we want to make as part of this module, but without .py extension. So now when the interpreter reaches line 6, it sees an import statement and so it jumps to that module, test.py in this case, execute all the statements in this file and then return back to main.py and resume the execution from where it left off. Now run main.py by right click anywhere inside the editor window and click run main. The program runs and the output gets displayed on the screen inside the run window. The first line shows the file that is executed by the Python interpreter and the following lines displays the output from the file. So you can see here that the output from the test module is displayed here as well, along with some other text that I will shortly describe. So now what if this output only makes sense in the context of the test module and is not relevant for main module? So in this case, to instruct the interpreter to skip all statements that only makes sense in the context of the owning module, this statement will come in handy. So if I copy this line from main.py file and wrap the print statement in the test.py file under this conditional header, then if we run main.py again, it simply skipped over the print statement this time. But if we run the test.py module directly, we will see the output on the screen. Moving on, line number 16 of main.py file is wrapped inside this condition as well. And this again ensures that this statement will only get executed if we run this module directly and not as part of another module. Here you can see that we are using the function name followed by the opening and closing parenthesis. This is a way to call the function we defined earlier. Additionally, we are providing some text during the function invocation that the function body is making use of as part of its text and displays the resolved text on the screen. Don't hang up on the syntax for now, it will get clear as we move on. Run the program and you will see the text displayed on the screen. So all this module does is display the text "Hi PyCharm" on the screen with the name dynamically added to the text and was provided to us by the caller of the function during the function invocation. If I change this text to say, "Thank you for watching this course," and run the script again, you can see that the output accommodates this change. Another thing worth looking here is that we can execute the program from this green icon as well. That will only be shown if we have this condition in our module. I stated earlier in the discussion that everything in Python is an object, and this is the time to put it to the test. For now, I would like you to think of an object as a container for data. We will revise or add to this definition of object as the course progresses. Moving on, Python comes equipped with a couple of built-in objects. These objects are classified to be either one of two types: simple objects and complex objects. Simple objects hold indivisible data, while complex objects are used to hold collections of data. Simple objects include int, float, and boolean, whereas string, tuple, list, dictionary, and set are considered as complex objects. I have also mentioned the sample value for each one just to give you a glimpse of the type of values each object can store. By looking at the sample value for string, one could have argued that isn't it that the string object should fall under the simple object category because the value it contains is a simple text that couldn't be further break apart. But the fact is that even though it looks like an indivisible data, the internal stir object implementation stores the string as a collection of individual characters. Furthermore, the Boolean object only stores two values, true or false. Next, we have further classified the complex objects based on whether the object is mutable or immutable. Mutable means that once we store the data to the object, it can be later modified in terms of extending the collection with new elements or by removing the existing ones. Whereas immutable means that once we store data to the object, it cannot be modified during the program execution. Furthermore, Python provides us with a built-in function that takes the value and return the type of object the value belongs to. So if I pass the value 42.6 to the type function, it returns the type float. Also, it is very common in programming languages to cast data between data types. That is to convert float data to int, or to convert int to a string, or to convert any object to any other object if it logically makes any sense. Python provides us with a built-in function for each one of these objects and are named exactly the same as the object name. So an int function to convert value to int, a float function to convert value to float, and so on so forth. Now let's jump to the IDE to put all these concepts to work. I have created a new file and name it object.py to demonstrate what we have discussed so far. The type function here takes a value as an input and return its type. And we further wrap the call to the type function inside print function to display the resulting type on the screen. Here I make use of some of the built-in functions to convert data from one type to another. Run the script and here are the results. As an exercise, I would like you to pause the video now and create a new file. Name it object.py and manually type the code shown here. Then run the script and examine the output for details. Variables in Python are used to hold references to values. This way, we define values once and refer to them from different parts of the program. This illustration will help to uncover the variables internal. The declaration of variables in Python is split up into two parts: variable name and the value on the right side of the assignment operator. Here you can see that we compare variables for both simple and complex objects. I have defined a variable total underscore employees and give it a value of 250 that pertains to a simple object. Python conventions dictates that the variable name must be all lowercase with multiple words separated by underscores. Down below is the illustration of the internal mechanics of how the variable gets bind to its assigned value. It is evident from the picture that a value of 250 is stored somewhere inside memory and that each value stored in the memory have some address assigned to it. Just to give you a rough idea, consider the memory address as 00996577 that actually gives identity to the value 250. Further, I demonstrate the fact that the variable name actually kept a reference to the memory address instead of holding the actual values. In other words, the variable total underscore employees points to the memory address where the value 250 is physically stored. If we were to compare it with the assignment of the complex objects, you can see that syntactically they are the same. The only reason I kept those separate is to illustrate the point that the values in the collection also hold references to its values instead of directly holding those values within. It can be seen from the figure that we have defined a tuple that pertains to a complex object with values 3, 6, and 7 respectively and assign it to a variable employee underscore IDs. Internally, Python reserves a contiguous block in memory to hold these three values, and the address to this block is copied over to the variable employee underscore IDs in the same way we have seen for simple objects. The thing that is worth looking here is that the reference to the complex object also hold references to its values instead of holding those values directly within. We can further validate this point by making use of the built-in ID function that returns the memory address of the object. Let's switch to the IDE to see these variables in action. I have created a new file and name it variable.py to demonstrate what we have discussed so far. Here you see that we create a variable total underscore employees and assign it to the value 250. Now each time I refer to this variable by its name, it resolves to the value it points to. Here we refer to the variable as part of the string in order to display the value on the screen. Now one thing worth mentioning here is that if the string contains a variable or any other expression that needs to be evaluated, it must be wrapped inside curly braces and precede the string with a modifier f to signal the interpreter that this string contains expressions that needs to be further resolved before displaying it on the screen. This built-in ID function returns the memory address this variable points to. Here we define another variable and assign it the complex object that hold multiple values and also print the memory address of that variable too. Here I validate the point that the complex object itself holds references to its values by comparing the ID of the value 3 and the first element of the complex object that comes out to be 3 as well. This is the way to get to the first element of this object. Please don't hang up on the syntax. It will get clear when we discuss complex objects later in this course. It turns out that the ID of both these values are the same, that further let us to think in a way that all simple values are stored only once, and each time we were to use the same value elsewhere, it resolves to an already existing value instead of creating a new value altogether. Here, since the Python is a dynamically typed language, we can assign a different value to an existing variable and it takes on that value from that point onwards in the program execution. Run the script and here are the results. As an exercise, I would like you to pause the video now and create a new file. Name it variable.py and manually type the code shown here. Then run the script and examine the output for details. Operators in the programming world are the characters or set of characters that execute certain operations. And Python is no different. Operators in Python falls into different categories with each one defined a well-defined purpose. The assignment operator is used to assign values to the variables as we did see earlier in the variables section. The math operators are used to perform math operations on its operands. These augmented assignment operators are to be used as a shortcut in cases where we have to modify the values of the variables. the comparison operators for comparing values, and conditional operators to evaluate multiple conditions that each comes out to be either true or false. Further, I have listed the operators by its evaluation precedence. The closer to the top of the table an operator appears, the higher its precedence. This means that if we have a statement that includes a couple of these operators, then these operators gets evaluated based on their precedence, with operators of higher precedence are evaluated first. Operators of the same precedence are evaluated from left to right except the assignment and the exponentiation operator that always evaluates from right to left. If we were to force the evaluation of some particular operators first, then we need to wrap that sub-expression inside parentheses. Now let's shift back to IDE to see these operators in action. I have created a couple of files to demonstrate the use of operators. Here you can see the assignment operator where we place the value to the right of the assignment operator and the variable we are assigning this value to on the left. Likewise, we have the mathematical operators as well that are performing math operations on its operands. In this case, one of the operands is a variable, and I mentioned earlier that the variables resolve to the value it points to. Since the variable value points to 10, so 10 will get substituted here in place of the variable name. Use plus for addition, minus for subtraction, asterisk for multiplication, double asterisk to raise the value of left operand to the power of its right operand. Use forward slash for division. The double forward slash refers to the floor division where the decimal part is chopped off from the result of the division and only the integer part is assigned to the variable. The modulus operator is used to return the remainder of the division. Here is the shorthand version to increment the variable value by 5. It's essentially the same as if we do it this way. Same stands true for other mathematical operators as well. Then comes the comparison operators for comparing values. I have defined two variables here and then compare these variables using different comparison operators. The double equals operator evaluates to true if both operands are equal or false otherwise. This evaluation is preceded by an if keyword that dictates that this line will only get executed if this expression evaluates to true, or else the interpreter will safely skip this statement. The exclamation mark equals equates to true if the operands do not match. The greater than and less than operators check to see if one operand is greater than or less than the other one. We can also check whether one operand is greater than or equals to the other by using a mix of greater than and equals operator. And likewise use the less than and equals operator to check if one operand is less than or equals to the other operand. The conditional operators make decisions based on a couple of evaluations. For conditional AND operator, for this expression to evaluates to true, all its sub-expressions must equate to true. If any one of these individual expressions evaluates to false, the overall expression will return false. Likewise, we have a conditional OR operator that returns true if any one of its sub-expressions returns true or false otherwise. The logical NOT operator negates the results of the expressions. So if an expression evaluates to true, using NOT in front of it flips the result to false and vice versa. Here we use multiple operators in a statement and these operators are executed based on their precedence. Since we know that the asterisk is of higher precedence than the plus operator, so 3 is multiplied by 4 first and the result of that operation is then added to 2 to get to the final value of 14. If we want to force the evaluation of the addition operation first, then it must be wrapped inside parentheses. This way, the addition operation happens before the multiplication operation, and the final results may differ for the two cases. As an exercise, I would like you to pause the video now and create a couple of files for each one of the operator types we discussed here, and manually type the code shown here in all the files. Then run the scripts and examine the output for details. Python provides us with a couple of ways to manage both ordered and unordered collections of data in memory. Ordered collections are used to store data that can be later referenced by its index position, whereas in the case of unordered collections, the order of the element is not guaranteed, and so we need to store some unique keys along with the values, and these keys will then be consulted to get to the actual values. Tuple is the simplest implementation of the ordered collection in Python. Tuples in Python are of fixed length and can hold elements of any data type. Fixed length means that once we define the tuple with values, it stays the same during the program execution. We cannot add new values to it, neither it allows to delete existing ones. This illustration will help to demonstrate the working of the data structures. Here we have defined a tuple that holds 12 elements, and that each element in the tuple stores the name of the month in order. Since tuples are ordered collections of data, so we can make use of the indices to store and later retrieve data from it. One thing worth looking here is that the indices starts from 0. So the first element in the tuple is at index position 0, second element is at index position 1, and so on so forth. Since the tuples in Python are of fixed length, so the Python interpreter requires that the values of the tuple are to be provided upfront and that it cannot be changed at runtime. If the requirement is to have a more dynamic data structure that can be extended to store more elements during the program execution, then list from Python is worth looking at. List data structure exposes an enriched API that we can utilize to store ordered collection of data that varies in size. Please be aware of the fact that the list is making use of tuple implementation under the hood, but the internal complexities of how this data structure deals with the intricacies of the tuple are all abstracted away from us. As you can see here, we have been provided with a couple of utility methods that allow us to store, retrieve, remove, and search for elements in the list. You can see for some of the methods that we are providing the index position as well. That further validates the point that these methods are making use of tuples under the hood, and so it is also considered an ordered collection in Python. Down below, I have illustrated the concept of a multi-dimensional sequence that is also supported by the Python programming language. Here we use the term sequence to refer to both tuples and list. Recall the definition of sequence from our earlier discussion when we talk about the Python jargon. Consider a multi-dimensional sequence as sequence within sequence. So to reach out to an element nested deep within the multi-dimensional sequence, we have to take our path inwards starting from the outermost element. So in this case, to refer to the element Georgia, we have to first look up for element stored at index 1 in the outer sequence, and then inside that element refer to the first element of the inside sequence by its index 0 to get to its value. In the case of multi-dimensional sequence, the outer sequence acts as a bucket to hold instances of the inner sequence and does not contain any values by itself. So in this case, the size of the outer sequence is 3, and each sequence element holds a reference to the inner sequence that is defined to be of size 2, primarily because we are storing US states with their capitals. One thing you might observe at this point is that the tuple or the list data structure only stores a single value that can be referenced by its index position. But what if instead of storing values by index position, we need to store values with distinct keys that acts as a metadata for the values. Python provides us with a dictionary construct that did exactly the same thing. It allows us to store distinct keys along with the actual values. And these keys are to be consulted to get to the stored values instead of making use of indices. Storing keys this way has the implication that it provides us with a glimpse of the stored values. To better understand the benefit of storing keys with values, take the example of a tuple that store custom objects that pertains to company employees. So each element in the tuple stores an employee object that wraps employee data like employee number, designation, salary, and other relevant details. So what if we are only interested in looking up for employee with some specific employee number? So in the case of tuples or list, we have to loop through all the elements, and for each element through the loop, we have to look up for employee number in the employee object, and only if we found the match, we will break out of the loop, or else we will continue looping until we found the match. Since employee number is unique for each employee, it can be used as a key to store with the employee object. This way we do not have to unfold each employee element for its ID. From the illustration, you can see that we have tagged the capital by its state. This way, if we were to look up for the capital of any particular state, all we have to do is to provide the state name to the get method of the dictionary API, and it returns the associated capital. Let's now switch to the IDE to see these data structures in action. I have created a new file for each one of tuple, list, dictionary, and another data structure set that we haven't discussed yet. This is the syntax to create a tuple. All elements defined by the tuple are required to be enclosed in a pair of parentheses, and that each element is separated from other elements by a comma. Commonly, all data elements in a tuple are homogeneous, meaning that they all pertains to the same object class, strings in this case. Then we assign the tuple to the variable months. Here we are referring to the eighth element of the tuple by using the name of the tuple followed by the index position in square brackets. Since the index starts from 0, so the eighth element is at index position 7. Here we demonstrate the syntax to define multi-dimensional tuple, where each element of the tuple is a tuple itself. And to refer to any element, we have to provide the index to both the outer as well as the inner tuple. I would like you to relate this piece of code with the illustration we have just went through. Beside tuples, Python gives us the provision to use list as individual elements of the tuple as well, and then refer to the list elements using the subscript notation in the same way we refer to tuple elements. This is the syntax to create a list. All elements are wrapped inside the opening and closing bracket, and that each element is separated from other by a comma. Since lists are immutable, so we can make use of its methods to insert new elements to the list or to delete existing ones. The insert method inserts the element at the specified index position, and the append method inserts the element at the end of the list. The insert method is costly because once we instruct the method to store values at some specific index, the index position is adjusted for not just the element that already exists at that index, but for all the following elements as well. Here we are deleting the last element from the list using statement that starts with the del keyword and is further making use of the len built-in function that returns the length of the passed in list. And because we know that the index position starts from 0, the last element should be at the index position that is one less than the size of the list. This is the way to extract a sublist out of a list. We need to provide the range of the indices in square brackets separated by colon. So this is a way to tell the interpreter that provide me all elements from the numbers list that spans from index 0 up until index 4, but please don't include the element that resides at index 4. So the element at the last specified index is not included in the new list. Please note that this operation does not harm the actual list, so it stays the same. We can also simulate two very important data structures using Python list API, namely stacks and queues. These are implemented as separate data structures in most other programming languages. Stack ensures that the last element added to it is the first one to be removed. So it strictly adheres to the LIFO principle, last in, first out. Consider a stack of books on the shelf. Now add one more book on top of it, and when you go about retrieving any book out of it, you have to first pick the book that you last put in. On the other hand, Q ensures that the first element added to it is the first one to be removed. So this data structure strictly follows the FIFO principle, first in, first out. Consider a queue of customers in front of the bank waiting for its turn. The first customer in the queue is the first one to be served by the bank teller. We can simulate both these behaviors by making use of the list API. We know from our earlier discussion that the append method add element to the end of the list, and there is a pop method that returns the last element from the list, and using these two methods we can ensure that the last element added to the list is the first one to be removed. Likewise, for simulating the queue behavior, we are again using the same append and pop method, but this time we are passing index 0 to the pop method, and this means that remove the first element from the list and return it. So append adds to the end, and the pop method with 0 index removes from the start of the list. Here I would like to discuss the list comprehension feature offered by the language. This is a compact way to create a new list from an existing one. We can take two actions for each element of an existing list before making it a part of the new list. Number one, we can change the elements by doing some computations on it. And number two, we can filter out the elements from the existing list to only make it a part of the new list if it satisfies certain conditions. Here you can see that the language has given us a concise and convenient notation to express these complex operations in a single line. First, since the result of applying these operations to an existing list would eventually result in a new list, so we must have to surround the statement inside brackets. Since we haven't gone through the looping and conditional constructs, so this expression may not make sense to you as of now, but will get super clear when we discuss these constructs in greater details later in the course. Just to give you an overview, this statement says that for each value in the numbers list, check to see if the value is greater than or equals to 5. If the value does not meet the condition, just skip it and not make it a part of the new list. Otherwise, if the value satisfies the condition, then go on and multiply that value by 2 and save the result in the new list. These steps are performed for each value in the source list. Next, think what happens if the source list contains hundreds of thousands of elements. So in that case, this copy operation certainly have a performance hit. So another option we have is, instead of eagerly evaluating the statement and immediately creates a new list, we can create a generator object out of it that produces values on demand. Wrapping the statement in parentheses instead of square brackets makes it to work as a generator function that produces values on request. Here is the multi-dimensional list with both list and tuples as its inner elements, and they work exactly the same way as we did see earlier for tuples. Dictionaries in Python are defined as collections of key value pairs that are surrounded by curly braces and further separated by comma. Each key value pair is separated by colon with key on left and value on right. Further, each key in the dictionary must be unique and it should pertains to an immutable object. Here we define a dictionary with month names as keys and the values are the number of days in that month. Since dictionaries are mutable objects, we can add new key value pairs to it or delete an existing key value pair. Please refer to the dictionary API for more details. One thing worth mentioning here is that we are now making use of the keys to look up for values instead of using indices as we did see for tuples and list objects. We can comprehend the dictionary object as well in the same way we did for list objects. Here we are calling the items method of the dictionary object that returns both the key and the value for each element. And then we create a new dictionary out of it by reversing the position of both key and value. This way, the newly constructed dictionary object will take this form. Set is another data structure in Python that we haven't discussed yet. This structure works the same way a list does, but with two major differences. Number one, set is an unordered collection of data, and so we cannot refer to its elements by its index position. And number two, it only stores a distinct set of values, and the type of objects it stores should be immutable. So if we add a value to set and this value happens to be already exist, then the old value is discarded and the new value is put in place. To create a set, wrap its elements inside curly braces and separate each one from the other by comma. Here we intentionally duplicate the string orange two times, but when we introspect the result of this print function, it turns out that the first instance of the string orange is removed from the set and the second one is retained. The implementation of set exposes an enriched API that we can make use of to do all sorts of things. Please refer to the set API for more details. As an exercise, I would like you to pause the video now and create a couple of files for each one of the data structures we discussed here and manually type the code shown here in all the files. Then run the scripts and examine the output for details. Python supports a number of conditional and looping constructs that allows us to easily control the flow of our applications. Consider the if construct as a conditional block of code that will only get executed if the associated condition evaluates to true. This illustration depicts the working of the if construct. We want to evaluate the grade of the student based on his final score. So we are passing in the test score as an input to the if construct. It checks to see if the score attained is more than or equals to 90 by using the comparison operator. If this evaluation comes out to be true, then the grade of the student is set to A and there is no need to go further and test for other conditions in the pipeline. So the control jumps to the next statement following the if construct by skipping all the other conditions that are defined as part of the if clause. However, if the score is less than 90, then the first condition becomes false and in that case the control falls back to check the next condition in the pipeline and so on so forth. So what if we have defined a couple of conditions and none of them evaluates to true? So then in that case, we have a catch all block that will get executed if it has not been caught up in any of the above conditions. Also, I have emphasized the fact that all conditions following the first one, including the last catch all part, is made optional by the language by surrounding it with a dotted rectangle and label it with optional. Now let's switch to the IDE to see this language construct in action. I have created a new file and name it conditional.py to see the if construct in action. Here we define the variable test underscore score and assign it the value of 75. Then we define a couple of conditions here. The first one is preceded by the if keyword and each subsequent condition is preceded by the elif keyword. That is short for else if. Then we have a keyword else that is not followed by any condition, and this serves as the catch all block. All these statements ends with a colon. This is a way to tell the interpreter that all the following indented statements makes a suite that will only get executed if the condition in the preceding statement evaluates to true. The style guide for Python code recommends a 4 spaces indents. So it turns out that because this condition evaluates to false, since the value of test underscore score is less than 90, this statement will not get executed and the control jumps to check the next condition in the pipeline. It also evaluates to false, so it jumps to the next one. And here it resolves to true. So the control enters the associated suite and execute this statement that displays this output on the screen. In case all conditions evaluates to false, then the control jumps to execute the statement that is associated with the else clause. This is a shorthand form of the if construct that we sometimes refer to as ternary condition. Here we define two variables a and b with values 10 and 20 respectively. Then here we create a new variable max underscore number and assign it with the maximum of these two numbers in a compact way. It perfectly makes sense if we read this expression in plain English. It says that assign a to the variable max underscore number if a is greater than b, or else assign b to this variable. As an exercise, I would like you to pause the video now and create a new file, name it conditional.py and manually type the code shown here. Then run the script and examine the output for details. Now let's make our way towards understanding the looping constructs offered by the Python programming language. These constructs help us out to iterate over the collection data. I have illustrated the two looping constructs on this slide. Choosing one over another is merely a personal choice. These include a for loop and a while loop. Let's discuss these one by one in the context that each is given a tuple to loop through that stores names of months. So the first one is the for loop. This is the simplest of the two loops in that the implementation of this looping construct provides us with the next element from the tuple each time through the loop without us explicitly tracking the index position of elements, which is essentially what we are doing in case of while loop. The while loop starts with the assignment of a variable with the initial value of 0, primarily because the tuple or list elements starts at index 0, as we discussed earlier in this course. Then a condition is evaluated that either equates to true or false. So in this case, a condition is made that checks to see if the counter variable is less than the total number of elements in the tuple. If it happens to be true, we have to look up for month from the tuple by making use of counter variable that represents the current index position and display the month that is stored at that index position on the screen. Then each time through the loop, we are incrementing the counter variable before evaluating the condition for the next iteration. So when we reach to the very end of the tuple, only then the condition evaluates to false, and in that case the program control jumps to the next statement following the while loop. So you can see that there is not much difference in the behavior of these looping constructs, except that in one case we are managing the index by ourselves, and in the other the index is managed for us. Now let's switch to the IDE to see these loops in action. Here you can see that I have created a new file loop.py in order to demonstrate loops in Python. So recall the workflow I just have illustrated and try to relate it with this code of chunk to clearly get an idea of what goes where and the order in which these pieces are called. Please do it for each one of the two loops. Here you can see that we have created a tuple and filled it in with the names of the months. Then we employ the for loop here to iterate over all the elements in the tuple. So it works in a way that each time through the loop, the variable month is assigned the next value from this tuple. It then makes use of this value inside the suite it owns, and when it is done with iterating over all the elements, the statements in the else suite are executed. This else part is optional. If it's not there, Python doesn't complain. Here we make use of the built-in enumerate function that returns not just the value but also the associated index position of the element in case it is required by the suite. Here we employ the while loop to iterate over the same tuple that stores names of months. You may notice that in this case we are managing the index position by ourselves each time through the loop and making use of this counter variable when referring to the tuple elements. Now what if we are not interested in traversing the whole tuple, but rather we would like to search the tuple for some specific element, and as soon as we find a match we need to get out of the loop and so not required to continue looping to the end. Also, there are cases where the requirement is to loop through all the collection elements, but each time through the loop, the inside code block may or may not execute to the end as the business logic dictates. Python provides us with a couple of branching constructs that does exactly the same thing. It provides us with the break keyword that signal the interpreter to jump straight out of the looping construct to the next statement following the loop, skipping not just the code following the break statement from the current iteration but also terminate the subsequent iterations as well. Also, we are provided with the continue keyword that allow us to only skip the current iteration and move to the next one. So this loop here is searching the tuple values for element 12, and as soon as it finds a match it sets the variable match underscore found to true and then break out of the for loop, and so it will not iterate over the remaining tuple values. One thing worth mentioning here is that the statements in the else clause will only get executed if the loop runs to the end. Since in this case a match is found and we left the loop before having to run it to the end, the statements wrapped by the else clause are not executed in this case. Here we are traversing this string one character at a time, and we are only interested in finding the number of occurrences of letter M in the whole string. So each time through the loop, we first check to see if the character is M or not. If the character is other than M, then we need not to execute this statement that adds 1 to the count each time it finds a letter M through the loop. So to skip over to the next iteration, we make use of continue statement in this case. So this statement will only get executed if the character happens to be an M. One thing worth mentioning here is that the string implementation provides us with a method named count that does exactly the same thing of finding occurrences of a particular character in a string. Functions in the programming world is a technique to group multiple statements together and further give it a name. This way, we can call a function by its name from different parts of the program, and all the statements it wraps around gets executed in turn. This greatly enhances the code reusability because we do not need to rewrite the same code each time we were to use it. Some functions operate on the data that is made available to it by the caller of the function during the program execution. Likewise, some functions return data to its caller, and the caller then makes use of this data in its processing. It is perfectly legal for a function to neither accept any data nor return anything out of it. Also, the function can both accept data and return data as well. Here I have created a function and name it print underscore me that wraps a single print statement that will only get executed when the function is called by its name. To define a function, we start with the keyword def followed by space, then the name of the function followed by a pair of parentheses and further end the statement with a colon. The conventions for naming functions in Python are the same as for naming variables. Then we indent all the statements that we want the function to wrap around by 4 spaces so that it becomes a part of the function and will only get executed when the function is invoked. This is called the function header and all its statements forms the function body. Later, we make a call to the function by its name. Function name followed by a pair of opening and closing parentheses is a way to tell the interpreter to go and execute the method body that is defined with this name. And please get back to me once you are done with executing all the statements. So from the interpreter perspective, when it encounters the function header, it skips the function body because it has been instructed to only execute the function when it is explicitly called from elsewhere in the program. Then when it reaches the statement that actually makes a call to the function, it jumps to the first statement of the function body and started executing all the statements that are defined as part of the function body. And when it reaches to the end, the control goes back to the caller of the function and the execution continues in the normal flow from there onwards. This is an example of a function that both accepts and returns data. We are passing a value to this function during its invocation, and the function definition exposes a variable to hold the passed in value. These variables acts as a placeholder for incoming data and are called parameters in object-oriented vocabulary. Likewise, the values that we are passing in to the called function are called arguments. So this function takes a value, doubles it, and then return this value to its caller. So when we call this function with value 5, the function doubles the value by multiplying it by 2 and then return the new value to its caller. To return value back to the caller, use the return keyword followed by a space and then the value that we want to return back to its caller. Once all the statements in the function body are executed, the control returns back to the caller of the function and the function call is substituted with the actual value returned from the function. Then we print the result we got back from the function here. If the result of the function is not used further in the program execution, then we can wrap the call to the function inline as part of the formatted string without introducing a new variable to store the function value. The string formatter first evaluates all the expressions that are surrounded within the curly braces, and once it resolves to a value, it will get combined with the rest of the string and gets displayed on the screen. We can pass both simple and complex objects to the function. Here you can see that we are passing the list as an argument to this function. And inside the function body, we loop through each list element and add each value to total variable using augmented assignment operator and finally return the accumulated value to its caller. If we want to have a function that can accept a variable number of arguments, then we place an asterisk in front of the variable name to let the interpreter know that during a call to this function, collect all the arguments that are passed during this function invocation and create a tuple out of it, and then assign that tuple to this variable args. Inside the function, we add all the values and return it as function return value. Here I have defined a function with two parameters, length and width. And this function returns the area of the rectangle by multiplying length and width. Now there are two ways to pass arguments to this function, by position or by keywords. Positional arguments map values to the parameters by their position. So the value 10 is assigned to length, and likewise value 20 is assigned to the width parameter respectively. If you want more control over this mapping process, Python comes with the keyword arguments as well. Here we need to be explicit and tell the interpreter that assign the value 20 to the parameter named width, and likewise assign the value 10 to the length parameter. One thing worth mentioning here is that all variables that we define in the function body, as well as the variables that are made available to us in the form of function parameters, are only visible within the body of the function. So once the function is done with its execution, all local variables are dereferenced and so available to be garbage collected. If you try to access a variable defined as part of the function body from elsewhere in the program, the Python interpreter reports an error. I stated in the very beginning of this course that Python supports functional programming as well. And I further go on to say that this paradigm gives the function the same power any other object in the language enjoys. So with this capability, the functions can be passed as an argument to other functions. Here I will be going to demonstrate it to you with two built-in functions from Python, map and filter. Both these functions accept function as its first argument and a list of values as its second argument. The map function provides each value from the list as an argument to this function and then add the value returned by this function to the new list. Likewise, the filter function also provided each value as an argument to this function, but in this case, the value from the source list will be added to the new list only if this function returns true, or else the value gets skipped and will not be added to the new list. One of the questions we have to answer with any programming language is whether the arguments we provide to the method are passed by value or passed by reference. Let's understand what these terms means. Passed by value means that the method actually creates a new local copy of the variable for each argument it accepts. In other words, a variable gets created with the same name as the parameter name and further initialize itself with the value provided by the caller of the function. This way we are simply cut off from the actual variable and started working with the local copy within the method code block. On the other hand, passed by reference means that instead of making a new copy altogether, the code inside the method block points to the actual values. And this has the consequence that any modifications made to the values of these variables inside the function body will have a global impact and hence resulted in modifications to the variables provided during method invocation. In Python, variables are always passed by reference. Don't panic if all we discussed so far seems daunting to you. I am going to further elaborate this concept by making use of this illustration. Here you can see that we are assigning the list to the variable employee underscore IDs, and later we call a function add employee ID and provide this list as an argument. Since the arguments are passed by reference, so the reference to this list is copied over to this parameter. Now both the local variable as well as the actual variable points to the same reference in memory, and any changes to the list inside the function body will get reflected in the global variable too. Now the value we are passing as an argument is a mutable list object. But what if we are providing an object that is immutable? So in that case, we create a new object out of this object plus the new values we want to add to this object within the function, and then return this new object from the method for further use. Strings in Python are used to hold character data wrapped inside either the single quotes or the double quotes. Python conventions dictates that choose either one of two and then stick with it. It is discouraged by the Python community to wrap the string inside single quotes at one place and to surround it with double quotes at some other place. We can concatenate two strings by making use of the plus operator when both operands are string. The Python interpreter concatenates them to make a new string altogether. Likewise, we can make use of the multiplication operator to repeat the string the required number of times. Also, we can compare two strings for equality using equality operator. I stated earlier in the course that consider an object as a container for data. But I also commit at that point that we will revise this definition of object as the course progresses. Now this is the time to add more to the object definition. Besides data, objects also contains methods that operates on data. Here we are calling the split method of the string object that breaks apart the string based on the white space character and returns the list with individual words of the string as its elements. Likewise, the join method takes the list as an argument and join its elements using the white space character. Now let's move on to discuss the object-oriented aspects of the language. The first in the list is encapsulation. This principle dictates that all complex functionality in the application should be hidden from its users. To better understand this concept, let's take the analogy of a coffee machine from the real world. To get a cup of coffee out of the machine, all we have to do is to choose our favorite beverage and press the button next to it, and by doing so, the coffee is made available for us. So all the inner workings of the coffee machine are abstracted away from us and instead provide us with a simple and easy to use interface to interact with the machine. Think what happens if we were to understand the inner workings of the coffee machine, like how the different ingredients are blended together and in which order. Also, what if we were to specify the quantity of each one of these ingredients, and only then we will be able to get a cup of coffee out of it. It is certainly going to be a mess. So encapsulation in the object-oriented vocabulary enforces the same rule that all complex functionality should be abstracted away from its users. We make use of classes and objects to achieve encapsulation in the object-oriented world. So what are the benefits gained when we break apart the monolithic code into separate classes as the business logic dictates? The first and the obvious one is that it makes the code simpler and easier to understand, since the code is now split up into multiple classes, and by doing so, each class hides its internal working from its users. Furthermore, it is now easier to locate and fix bugs because the scope of the error is now narrowed down to individual classes instead of us lingering around the monolithic code. To better understand the concepts of classes and objects, this illustration will help demonstrate it to you. Take the analogy of the bulb factory from the real world that manufactures and produces bulbs for its consumers. Once produced and delivered, each bulb manages its own life cycle independent of others. So it will never be the case that switching one bulb off is going to switch the other bulbs off too. So the state of each bulb is managed independently. In the object-oriented terminology, consider the class as a factory or more precisely as a blueprint from which individual objects are created or instantiated. Once created, each object will have its own set of fields, which we call the instance fields, and a set of methods, which we call the instance methods. These are called instance fields and instance methods because they are bind to the individual objects, and we have to consult these objects for their values. Another reason why we name it this way is because there are some fields and methods that only make sense in the context of the class and not to individual objects, and we have to reach out to the class for their values. For example, in order to get a count of how many bulbs are produced by the bulb factory so far, we have to consult the bulb factory for these details and not have to go to the individual bulbs. Likewise, we have to reach out to the class to get a count of the total objects instantiated from that class. You might have observed that the production count field and get production count method are not made available to objects as their purpose is intended to be confined to class only and does not make any sense for individual objects. In object-oriented vocabulary, we call the fields and methods that are available to class only as class fields and class methods respectively. So organizing code into classes not just makes the code organized, but it also helps to achieve encapsulation because we wrapped all the complex functionality inside these methods and exposes these methods as interfaces to the outside world. Only the developer who creates the class will have to know the internal workings of the class. We as a consumer will not have to bother went inside the class code for details. We just have to call the exposed methods and get back the results. Let's now switch to the IDE to see these classes and objects in action. I have created a couple of files to demonstrate the workings of classes and objects in Python. This file creates a class named bicycle for encapsulating the bicycle state and its associated behavior. To define a class starts with the keyword class followed by the class name, bicycle in this case, and is further followed by a colon, and then the code block owned by the class, indented by 4 spaces. For now, let's try to relate each and every piece of code in this class with the concepts we just went through. So here we define the class field, the field that only makes sense in the context of the class. Here we define a method named init that is preceded and followed by two underscores. The methods named this way are called special methods or magic methods because these methods are called implicitly by the Python internals based on its context. Here the init method is called each time a new object is constructed from this class to give us an opportunity to define and initialize instance fields that are bound to the objects and also to do other prep work before the object is ever made available for its consumers. Since the init method is called during object construction, we also call it a constructor method. Now, when we say that the init method is used to define instance fields that are bound to the objects, the question here is that how do we get a reference to the newly constructed object inside the init method in order to define new instance fields on it? The answer is that the object is provided to us by Python as the first argument to this constructor method, and by conventions it is named self. The other parameters are the ones that we explicitly provided at the time of object construction, as we will shortly see. Inside the constructor body, we have defined the instance fields by associating them with the current object using the dot notation. Object name, dot, and then the instance field, and further initialize them with the incoming data. Since we are constructing a new bicycle, we must have to increment this class field as well so that it correctly reflects the total number of objects created from this class so far. Since class fields are bound to class itself, we must have to access or modify it in the context of the class by associating the class field with its class name separated by dot. Also, you can see here that we are assigning unique ID to each object by creating a new instance field BID and gets its value from the class field that acts as an object counter. So initially number of bicycles is set to 0, and whenever an object is constructed, this field is incremented by 1 and assign this value to the BID instance field. This way the class field not just keeps track of the total objects constructed from this class but also provides a unique value to each object along the way. One thing worth considering here is that the init method is made optional by the language. If we do not include it as part of the class, it will never get called. So how do we define the instance fields then? It turns out that the other way to effectively define instance fields is by making use of the getter-setter methods. So it works in a way that we define a getter-setter pair for each instance field, and the conventions for naming these methods dictates that both methods should include the field name but preceded by get underscore and set underscore respectively. One thing worth mentioning here is that all methods that we define as part of the class must have self as its first parameter unless we explicitly mentioned not to do it this way. Moving on, since the setter methods are used to define and initialize the instance fields, we can provide the values that the instance fields will get initialized to during the method invocation. One thing you may have noticed is that we are not passing the initial value for set underscore BID method. The reason is that we are consulting the class field for the unique ID in that case, and so it doesn't make sense to pass any value to it. So we can make use of either the init constructor method or the individual getter setters or both to properly construct our object. All methods we discussed so far are called instance methods because they all work with the instance fields and is further confirmed by looking at the first argument to the method named self, that is the handle to the object itself. Recall from our earlier discussion, besides instance methods, we can have the class methods as well that are not meant to be bound to individual objects. To define class methods, we have to annotate the method with the add class method decorator. This is a way to tell the Python that please consider the following method as part of the class and provide a reference to the class here in the parameter instead of the object. So up until now, all methods we have discussed so far are something to do with the object construction. Next, here we define two methods that actually encapsulates the behavior or the complex functionality of the object. These methods are meant to transit object from one valid state to another. In other words, these methods act upon the object state as per the business logic dictates. So in this method, you can see that we are changing the state of a bicycle object by decreasing its speed, and this method goes the other way around and increases the bicycle speed by the provided factor. Now here are the two ways to construct an object. The first one is making use of the constructor, and the second one is by making use of the getter-setter methods. Once done with the constructing part, we are calling the methods on the object that eventually results in transitioning the object from one state to another. Please pause the video for now and try to get yourself familiarized with the way we are constructing objects and later making a call to its methods. One thing worth mentioning here is that the Python community encourages the use of init constructor method in favor of individual getter setters, primarily because it adds to the developer convenience to define all fields at one place instead of explicitly calling each setter method in turn. As an exercise, I would like to request you to please create this program on your own, execute it and see how it goes. Now let's talk about the remaining two object-oriented concepts, inheritance and polymorphism. Inheritance is all about reusing the existing class features in other classes. This way, all the common functionality is wrapped inside a class, and the reason of existence for this class is primarily to package up the common features and make them available for other classes to add more specialized features on top of it. In Python vocabulary, the class that exposes the common functionality is called the superclass, and the classes that inherit that functionality is called the subclass. So here in this figure, you can see that we are encapsulating the features that are common to bicycles into a bicycle class and let the specialized bicycle classes extend their common features from this bicycle class plus add their own. So you can see here that the mountain bike add suspension property in addition to what was made available to it by the bicycle class, and the road bike class adds specific tire width property. Let's now switch to the IDE to see this inheritance in action. We have created two more classes in the project, a mountain bike class and the road bike class. Both these classes are extending the bicycle class that we created a short while ago by enclosing the class name bicycle inside parentheses right after the class name magically makes all the fields and methods of the bicycle superclass available to its subclasses as if they are defined as part of these classes. In addition, the language has given us the provision to redefine the inherited methods from the superclass into its subclasses in case the method implementation doesn't make sense for any of its subclasses. So in that case, we can define the same method that we inherited from the superclass into its subclass to provide more specialized implementation that best suits the subclass. This way of redefining the inherited methods of a superclass by its subclasses is called method overriding in object-oriented parlance. If the requirement is to simply add to whatever was made available by the superclass method, we can call the superclass method from the subclass by making use of the super keyword. Here you can see that inside the init method of the road bike class, we are calling the init method of its superclass bicycle using this statement. This is a way to tell the interpreter that call the init method of the superclass bicycle, and during method invocation pass this object as first argument to this method. So when the init method of the superclass is called, the first parameter self refers to the subclass object and not the superclass object, which is the default behavior. Here we are calling the print underscore description method of the superclass in the exact same way. Python adheres to the multiple inheritance model. This means that a class can extend from more than one superclass. This has the implication that we may run into a diamond problem where the fields or the methods of the same name coexist in multiple superclasses. Shown here is the illustration that depicts what went wrong if the language supports multiple inheritance. So in this case, you can see that the employee customer class has no means of differentiating between the inherited methods with the same name that coexist in both the superclasses. So to counter this, Python employs a depth-first approach. It first looks for the requested attribute in the subclass. If it is not there, then it introspects the first superclass, and if the attribute is not there either, then it moves on and consults its superclass, person in this case. If it still doesn't find the match, then it takes on the second superclass and traverses its node in the exact same way. One thing worth looking here is that the person node is consulted twice for attributes. So Python further goes on and normalize this path by only considering the last occurrence of the repeated nodes and simply skipping over from its previous occurrences. Another way to achieve inheritance in Python is by making use of abstract classes. Think of abstract classes as defining the specifications that the subclasses must implement in order to be fully compliant. Here you can see that we declare a couple of methods in the vehicle abstract class and that these methods differ from the other methods in that we are not providing the method body for the abstract methods in the superclass. We only specify the method name and the parameters it accepts in the superclass, and it's up to the classes that inherits this superclass to come up with their own implementation of these methods. So in this case, the bicycle class will implement the methods the way it works for bicycle, and the same is true for motorcycle as well. Once a class extends an abstract class, it is bound to provide the implementation of all abstract methods declared in the abstract class. There is no way to escape out of it by implementing few methods and left others unhandled. Let's now switch to the IDE to see these abstract classes in action. We have created an abstract class here and name it vehicle.py. Next, we have declared a couple of methods that we would like the inherited classes to implement. Now to tell the Python interpreter that this is an abstract class, we have to add the keyword parameter inside parenthesis next to the class name with key as meta class, and the value is the attribute ABC meta from the ABC module. Remember to import the ABC module at the very beginning of the file before referring to its attributes here. Furthermore, we have annotated each abstract method with the abc.abstract method decorator. Also, we have added the return keyword for each one of these methods to signify that these methods only make sense for its implementing classes and does not make any sense in the abstract class. In addition, once we declare a class to be an abstract class, it cannot be instantiated. So we cannot create new objects from this class. In addition to the abstract methods, the abstract class can have the implemented methods as well, that the subclass inherits the same way it inherits functionality from a non-abstract class. So using abstract classes in order to restrict its inherited classes to always provide the implementation of the abstract methods has the implication that we can later call these methods without having to know the object on which these methods have been called. Since we know that both mountain bike and road bike are extending the vehicle abstract superclass, so we first create a couple of instances of these classes and then call the speedup method for each one of these objects in a loop without having to treat each object individually. This way of calling same methods on multiple objects that belongs to different classes is called polymorphism in object-oriented vocabulary. Runtime errors in Python are the ones that are syntactically correct and will only get emerged and breaks the application at runtime. To anticipate runtime errors that might have originated during the code execution and to elegantly deal with it, Python provides us with a try except construct. So all the offending code that may cause the application to break will be wrapped inside the try block, and the subsequent except block will then deal with the exception in case something went wrong when executing the statements in the try block. So each time an error occurred inside the try block, the Python interpreter checks to see if there is any except clause that is meant to deal with that exception type by looking at the error type next to the keyword except. If it finds one, then it executes the except block to gracefully deal with the reported error. At this point, one may have argued that how do we know the type of error this code might have raised in order to explicitly mention it over here beforehand? The answer is that we have to first execute the offending code without wrapping it in a try construct just to know the type of error this code might have resulted in and then mention it over here. Here you can see that we are creating a tuple with three elements and then later refer to its fourth element at index position 3 because of the fact that the index position starts at 0. Since the tuple is defined to be of size 3 and we are requesting the element that exceeds its range, the Python interpreter reports an error that we caught up and display a more user-friendly error on the screen. Further, we have two more clauses as part of the try except construct. These are else and finally. The statements wrapped by the else clause will only get executed if the statements in the try block does not report any error. Whereas the statements wrapped by the finally clause will always get executed even if an error occurs in the try block. Handling exceptions this way has the implication that the script will continue to run to its end. In contrast, if we do not deal with the exceptions using these language constructs, then the program breaks as soon as an error occurred and the following statements will not get executed. So we are finally reaching to the end of the course. I would like to thank you for your time to watch it to the end and hope that this course takes your understanding to the next level. Before I say goodbye to you, I would like to request you to please subscribe to this channel for latest updates. Goodbye and see you in the upcoming courses.